So today I'd just like to give you an overview of the approach that I've been implementing as part of my PhD. So I'm going to first introduce the concept, the idea of fitting simplified kinetic motifs and using continuous flow. I know that the battery reactor is historically what's used within the pharmaceutical industries, but what flow offers is that completely different operating region. So it gives you very precise, short resonance time, access to high temperatures and pressures, which you would otherwise not be able to access. So now we have the whole process window that we can access, but actually, normally we observe that we form some sort of impurity. So straight away, we know that things like a change in heating and cooling rates at scale will have an effect on product quality and outcome. We know that addition times will have an effect. We know hold times will. So straight away, when we scale up, we're likely to see more variation. And one thing we want to do, to the best of our ability at the small scale, be able to predict how our input parameters will affect the output and what variation are we allowed, and what will let us operate our process within specification and what will not. So this is a typical trace that you'd expect for a reaction. So your starting material goes down, your desired product goes up, but at a certain point, your reaction will overreact to form an impurity S. So to normally try and understand this, what we'll do is we'll say, well, we have got to feel that these different input parameters will have an effect on our process: time, temperature, concentration, and we'll study these within a certain region. So with this is a face-centered cubic design. So this is an experimental design based on understanding the main effects, the curvature effects, and the interaction effects. And from this, we'll generate a model. So within this, I've highlighted the region of study. So generally with an experimental design, you focus on the reaction endpoints. And from this, you generate a polynomial model. And from this, what I've tried to do is plot a typical polynomial that you'll generate. And as you can see, within the region of space that you studied as part of the experimental design, the polynomial predicts it excellently. But actually, the moment that you extrapolate either side, actually the mathematical model generator breaks down. And the reason for this is that we're not using any of our existing knowledge about the chemistry really to generate this polynomial model. And the polynomial model really does assume no prior knowledge of the reactor or reaction. And most of us are chemists and chemical engineers. We have a good idea of how we expect this process will be taking place. So what we believe is that we should use this to generate the models to predict reaction output. And then because we're using the intrinsics of the model, that would let us extrapolate better. So really, there are benefits of fitting design of experiments. You don't need a lot of knowledge. One key thing is that it's good from a quality angle because it lets you predict interdependencies and interactions between input parameters, and it helps demonstrate robustness within constraints. But then on the other hand, it focuses on the desired reaction endpoint typically. And a lot of the time, say in this system here, within this set of constraints, we don't actually understand much about our impurity formation, which is fine on a small scale when actually we can handle things pretty quickly and work them up and purify them quickly. But when we scale up, where we might leave our battery reactor holding for a few hours, then actually these might over time increase. So we want to know at what point does the impurity that we form start to impact on our process performance. So this is just trying to summarize the type of fitting approach. So this I've adapted from a previous DynoChem webinar. So what you do is you input your initial postulated motif. And the good thing about DynoChem is you don't need to solve or come up with any of the maths. You can just input your idea of what you think is occurring. So you can just a simplified type of, I think, molecule A is reacting with molecule B to form my product, but I think my product might be decomposing, and that type of approach, rather than get bogged down with the mathematical modelling side. And then from this, we put in initial guesses, and then we minimise the sum of squares. So we go from a maxima to a minima. And if we obtain a good fit, clearly we'll use that kinetic model that we've generated to optimize our process and to identify where we might want to operate. If we have a lack of fit, we'll try again. We'll try a different motif and see if that improves the fit to the experimental data.